Okay, well, we have added complex numbers and subtracted them. We've multiplied them. What's left to do is divide them. This might be the most work, but it's basically just a little bit of extra algebra. Remember, we're basically going to be looking at fractions where you have a complex number on top and a complex number on the bottom. So all you need to remember is that when you have something like C over D, the D is a fraction bar. The fraction bar means divided by. That is C divided by D. So we're going to look at fractions where we have a complex number over a complex number, which clearly that means they're not written in the correct form. We need them to be looking something like this when we're done, where we have a number plus a number times I. So we're going to divide or simplify these fractions, and we're going to write them in standard form. So I'm telling you right here how to do it. All we must do is multiply both the numerator and denominator of each fraction by the complex conjugate of the denominator. So I'm going to multiply this by, really I'm multiplying it by 1. Just like 8 over 8 is equal to 1, or negative 6 over negative 6 is equal to 1. I'm going to multiply this by, let's see, what is the complex conjugate of this denominator? 1 plus I. It'd be 1 minus I, right? Oops. 1 minus I. 1 minus I. Well, in case you're wondering, of course this is equal to 1. Anytime the numerator and denominator are equal, this is equal to 1. So we're not changing the value whatsoever. And when we're done with this multiplication, we're going to be able to write it in a plus bi form. And the reason that works is when you multiply fractions, you multiply the top and you multiply the bottom. When you multiply the bottoms together, they're complex conjugates. So remember what's going to happen when we multiply complex conjugate pairs together? We get a real number. And you might remember, maybe I'll do the denominator first. What happens when you multiply complex conjugate pairs together? I'll put parentheses around them just to remind you what we're doing. Remember that when you FOIL it, the inner and outer cancel out, and we end up getting 1 squared plus 1 squared, because A is 1 and B is 1. Or even if you take B as negative 1, it doesn't matter, because when you square it, it becomes positive. So the denominator is 2. I'll let you, if you forgot that, go ahead and FOIL this out, and you'll see that you get 1 times 1 for the first, outer and inner cancel out, and then for the last you get negative I squared, which is negative 1. Negative 1 times negative 1 is a positive 1. Okay, and here we'll need to distribute. So on top I can multiply 2i by 1. That gives me 2i. And then 2i times negative I, positive times negative is negative, 2i squared. So we're still not done because we have an I squared, which we should never have as a final answer, because I squared is equal to negative 1. So this really becomes, instead of negative 2i squared, or instead of minus 2i squared, it's going to be plus 2, because 2 times I squared gives you, it is 2 times negative 1. So we're really getting two negatives canceling out into a positive. So that's equal to 2i plus 2 over 2. Now let's write the top in the correct form, 2 plus 2i over 2. And I generally, well, not for this problem. This problem can be reduced. Why can it be reduced? Because 2 can cancel with both of the terms. It has to be able to cancel with both of them, remember? What I'm going to do is factor a 2 out of the top, and that would give me a 1 plus I all over 2. And if you, just as a review, remember, if I go backwards and distribute here, I get 2 times 1, which is 2, 2 times I, which is 2i, 2 plus 2i. And now I'm going to cancel the 2. And your final answer, 1 plus I. Much nicer than this more complicated looking 3. Wow, that is really interesting. That 2i over 1 plus I is equal to 1 plus I. That doesn't happen very often. All right, so let's look at the second one. Okay, so the second one, we've got the denominator is 3 plus 4i, so we have to multiply top and bottom by the complex conjugate of the bottom. So 3 minus 4i over 3 minus 4i, that is all equal to 1. So when we do the multiplication, we're going to get an expression that's absolutely 100% equivalent to this. And I'm going to use the shortcut here. If you've forgotten again, I'm just going to remind you that a plus bi times a minus bi is just a squared plus b squared. We did that in the previous video. So this bottom is really 3 squared plus 4 squared. Now that only works when you're multiplying two complex conjugate, a complex conjugate pair. 3 plus 4i, 3 minus 4i. So that's going to end up being 3 squared. Well, I'll worry about that later. Let's do the distributive property again. 2i times all of this. So it'll be 2i times 3, that's 6i. 2i times negative 4i is negative 8i squared. And pretty soon you're just going to get used to remembering that minus 8i squared is just plus 8. So 6i plus 8, because I squared is negative 1. Over, and what is this? 9 and 16 is 25. All right, so let's write the top as a standard form, which would be 8 plus 6i over 25. Now, I generally accept this as a final answer, as long as it's reduced. I mean, if this were a 5 plus 5i, and you had a 25 underneath here, you could do some reducing. But as long as you have a complex number in a plus bi form over a real number like this, I'll accept this. The preferable way is writing it like a plus bi, which means you break this into two fractions. This is equal to, after all, 8 over 25 plus 6 over 5 times I. I prefer this. This is the correct form, a plus bi. But if your final answer is a plus bi over 3 or over 25, I'm not going to take any points off for that. But you need to know, if I ask you what the real part is and what the imaginary part is from this, you need to know that a is not 8 and b is not 6. It's 8 over 25. Here's the real part, and 6 over 5 is the imaginary part. Okay, let's do one more like this. Actually looks a little bit easier. Negative 3 divided by I. What's the complex conjugate of I? Well, I is 0 plus I if you wrote it in a plus bi form. We never write it like this. We never write the zeros, but we could write it like that. So a 0 minus I would be the complex conjugate. So we'll multiply by 1 in the form of negative I over negative I. And that gets us, on top, it's going to be a negative times negative is positive, so we get 3i on top. And on the bottom, I times negative I is a negative I squared, which is 3i over negative 1, because I squared is negative 1. So the denominator is just 1. So negative 3 divided by I is equal to 3i. All right, well, the next one, we are simply going to evaluate an expression we're going to evaluate x squared plus 19 divided by 2 minus x when we're told that x has the value 3i. So all we need to do is replace each x with 3i, and I would put it in parentheses, at least on this one where you're squaring it. So x squared becomes 3i in parentheses squared plus 19 over 2 minus 3i. I don't have to put that 3i in parentheses. And what do we get? What is 3i squared? It's 3 squared, I squared. I squared is a negative 1. So I'm gonna leave that little interim step to you, but make sure you understand why what I'm putting the box around is equal to negative 9. Because it's 3 squared, I squared. 3 squared is 9, I squared is negative 1. Plus 19 over 2 minus 3i, and that is equal to 10 over 2 minus 3i. Well, that's certainly not the form we want it to be in. We want it to always be in the form of a plus bi, not 10 over a plus bi, or 2 minus 3i. So I'm going to take this and multiply it by 1. And by 1, I mean I'm going to multiply it by the complex conjugate of the denominator on top and bottom. So that would equal 1. So 2 plus 3i, 2 plus 3i. Again, this term right here is just the number 1, so it's not changing the value at all. Now let me continue right here. Well, what's the denominator going to be when we do this multiplication? 2 minus 3i, 2 plus 3i. The shortcut just tells us it's 2 squared plus 3 squared. 2 squared plus 3 squared. And then when we do the distributive property on top, again, we're doing 10 times 2 plus 3i. 20 plus 30i. Oops, 30. 20 plus 30i. And what is the denominator? 2 squared is 4, 3 squared is 9, so 4 and 9 is 13. 20 plus 30i. And once again, we have a complex number divided by a real number. And there's no canceling that could go on here. We can't reduce this at all. My preferred way of writing it would be 20 over 13 plus 30 over 13 times I. And maybe, since I prefer that way, I'm going to write it that way. Actually put it in a plus bi form instead of a plus bi over 13. So I'm going to have to go to the left here and get a little bit more room. 20 over 13 plus 30 over 13 times I. So for a plus bi, the real part is a, so the real part is 20 over 13, and the part that's multiplied by I is the imaginary part, b, which would be 30 over 13. All right, to finish up this video, we got one more thing to do here. You probably remember this. For any positive real number b, the principal square root of b is simply radical. Principal square root means you use a radical b. But the principal square root of the negative number negative b is defined like this. But what will never leave an answer like this, ever. Remember we said earlier that that is equal to radical negative 1 times radical b. We didn't use that one exactly, but something similar. And radical negative 1 is an I. That's equal to I. So this is equal to I radical b. Or you could write it radical bi. Most textbooks, most people using complex numbers, when they have a radical, they tend not to write it like radical bi. Can you see why? based on how I wrote that? Is it absolutely clear to you whether this I is under the radical or not? It's kind of on the border, right? If you put the I, it shouldn't be. I didn't want it to be under the radical. That's why we write it in this order. You can put the I in front of it. But I will absolutely never mark it wrong if you do this. Radical B, I. Just make sure the I is not underneath the radical. So all we're doing here, let's take a really simple example. Radical -7, the principal square root of -7. Again, we're dealing with complex numbers. This is not a real number at all, because in real numbers you can't have a negative number under a radical. So that's equal to I times radical 7. You can think of it as radical -1 times radical 7. Anytime you have the negative number under the radical, pull it out and make it an I. Let's do another one. Let's do one that simplifies even more. This is 1. What's this going to be equal to? That's 4i. Why is it 4i? Because you can think of it as this. We broke it up into the negative sign. We pulled out the -1, so to speak, and put it under the radical, and that left us with a 16 under the radical. This is I, this is 4. And we'll pick this up in the next video and finish up our discussion on complex numbers.